Exam 3 is a week from today. And the topics are everything up through stresses and beams. Yeah, and including one that we're going to get to today. So on Monday we did round circular cross sections. Now today we're going to do thin walled tube cross sections, and those will both be on the test. And remember that exams are cumulative, so be sure you go back and look at old stuff too. All right, so this is number 3. We have a steel beam. It has a huge mass. Has a hollow circular cross section, and it gives the dimensions. And we want to calculate the. Well, I didn't. There must be more to this problem because there's no point A listed. Okay, so the point A is all the way on the left end when you're looking down the beam from the right end. So this would be like all the way in the positive Z direction. And then strain, maximum shear stress, all that stuff. Okay, well, the first thing we have to do is calculate the external loads. We have applied loads, a couple of 800 Newton meters here. And at the right end, we have a 2,000 Newton force and a 600 Newton meter couple. All we have is horizontal forces and x-axis couples. And so the only external loads that there are going to be, oh, it also said, oh my gosh, okay, that's not true. We have to deal with the mass too, with the weight. So let me move this around. So I'm going to put this down here. And we also have a distributed load due to the weight. And the total weight is 200 times 9.81. The total length is 0.8 meters. So the total weight is 1962 newtons. And then we're dividing that by 0.8 to get the distributed load. And you have a distributed load of 2452.5 newtons per meter. And then over here, this is a fixed joint with the wall. So we have a reaction force R and a couple MR, and then a torque, fancy TR. Any questions about that free body diagram? And now I'm going to represent that distributed load as a point force. Well, that acts right at the midpoint. I already figured out the total weight is 1962. Over here we have R, MR, and TR. And then we have the couple here of 800, the 2000 Newton force, and the 600.
By then, the load is greater than just applying the weight.
The weight is, so the total weight is 200 kilograms times 9.81. Eventually, when we do our cuts, we're going to have to treat that as a distributed load. So I got the distributed load by taking the total weight, 1962, divided by 0.8. The length is 0.8. Yep. And I'll put my about point over here. So Newton's second law says Rx, Ry plus 0, negative 1962 plus 2000, 0 is equal to zeros. So that force R is negative 2000 for the X component and positive 1962 for the Y component. Any questions about that? And then the moment equation about the Z-axis, we have MR, that's just added on because it's a couple. At the midpoint, we have a moment arm of 0.4 because the whole length is 0.8 and a force of 1962. And that downward force would cause a rotation clockwise. So we want negative there. And nothing else produces moments about the Z-axis. So this is equal to 0. And so that reaction couple is 784.8. And then the moment equation about the x-axis, we have fancy TR, negative 800 and negative 600. That all adds up to 0. And so TR is equal to positive 1400 Newton meters. Yep.
When you chose the about point was to the right instead of the left. Did that change?
Yes, exactly. That's exactly right.
So I guess it would have changed to like a negative direction.
So if my red dot was over at the right end, you always think about the body being rotated around your about point, so this downward 1962 would make it rotate counterclockwise then. So it would be positive. It would happen to have the same moment arm in this case. It would just switch from negative to positive. Okay, so now we have all the external loads, and halfway, the X value we want is halfway between the wall and the beam's midpoint. So we're looking for a point here. And on the cross section, we're looking for it here, where the z-axis is this way, the y-axis is this way, and x is coming out towards us.
What do you know the position of on the quest
I didn't copy that figure, but that a figure just like this is given in the problem. All right, so since it didn't ask for for the full internal load functions, we don't have to do it as a function of x. We can just do the one cut at the one x value we want. Saves a little effort. That is going to be, so how much weight is this going to be? If we do our cut like this, what's the weight force going to be?
613.125.
Is that, so yeah, 1962 divided by 4, yeah. So, right, 613 something. And so actually, in this case, we're never going to have to use the distributed load. We can just, well, I'll get to that in a second. So we're going to do just one cut. And this is going to be for a single x value of 0.2. That is this distance. And so this whole length is 0.2. We have a weight acting down from the middle that's just a quarter of the full weight. So this is.
Is it 490.5? Yeah.
Oh, okay.
I calculated the distributive load a fourth of that, but you want a fourth of the weight.
Oh, it would be, so if you do the distributed load,
that's where I got the 600.
It would be the distributed load times the distance of 0.2 instead of a quarter of it. Because the distributed load is a force per distance. So if your distance is 0.2, you multiply times 0.2. So 490.5, you said? Okay. And then we have our force vector R of negative 2,000, positive 1962. And we have our couple of 784.8. And we have our torque of 1400. And we haven't made it to, we haven't made it to the 800. So the only other loads acting are the internal loads, P, V, M, and fancy T. Newton's second law. I'm going to do my about point at the left end like I always do with cuts. Negative 2,000, 1962, plus 0, negative 490.5, plus T, negative V, is equal to zeros. So T is equal to 2,000. V is 1471.5. And then the moment equation about the z-axis, we're adding on this 784.8, because that's a couple. And then we have, go away, plus or minus. So So the whole thing is 0.2. So the distance from the about point to where that weight force is applied is 0.1. The force is 490.5. And that's a clockwise moment, so we want the negative. And then plus m minus v x, and x in this case is 0.2. And this is equal to 0. So m is equal to, let's see. So we got the negative 784.8 and the plus 49.05 and the plus 1471.5 times 0.2. So 294.3.
Is it 490 or 4?
It was 490.5 times 0.1 gives you 49.05. This should be 294.3. And so you get m is equal to negative 441.45. And then we'll do, yeah,
Question around the full body diagram.
yeah, free body diagram.
The T to the right. The torque.
Yep,
How did you know what direction to put?
that's an internal load. So we just know that, I mean, our sign convention is just that's always pointing to the right if we're working from the left end, like we always do. So we always put that internal torque going to the right. And the sign will just come out on its own. Okay, so now we're adding, we have a positive 1400 plus T, fancy T, is equal to 0. Those are the only couples in the x direction. And so here's one where, you can see we assumed that fancy T is going to the right. It turned out it was negative, so it's really going to the left, but it'll tell you that when you do the calculation. So T is equal to negative 1400. Okay, now we have all those internal loads. So now we can start calculating those stresses. So we're going to calculate the stresses at that point A. So first, so we know that the total is going to be the stress tensor due to the internal tension plus the stress tensor due to the bending moment plus the stress tensor due to the shear force plus the stress tensor due to the internal torque. So I'll start with the stress tensor due to tension compression. We know that that's a X normal stress, and it's equal to the internal tension of 2,000 divided by the area. The area is the area of the outer disk minus the area of the inner disk. Those radii are 0.012 and 0.01. So we have that the area is pi times 0.012 squared minus pi times 0.01 squared. Did I get those right? Yes. And so that is an area of 1.3823 times 10 to the minus fourth meters squared. And so the X normal stress is 2,000 divided by this, which is 1.4469 times 10 to the 7 pascals. And so the stress tensor due to tension compression is 1.4469 times 10 to the 7, zeros everywhere else. Okay, so now we're going to the stress due to the bending moment. And I think it's always a good habit to remind yourself, like, look at the shape of the cross section, think about the problem. Does this meet the beam requirements for this calculation? You know, there are times when you can calculate stuff, you have the ability to plug numbers in and stuff, but those formulas do not work for the cross section that we have. Okay, so let's go to the stress due to the bending moment. What are the beam requirements for calculating the stress due to the bending moment for us?
Straight, and you're straight, prismatic, and
Yeah, perfect.
symmetrical and white.
Great. Yep, exactly. There's 3 requirements. It has to be straight. It has to be the same cross section all the way down, prismatic. And it has to be symmetric about the y-axis. This meets all those requirements, so we can go on with the calculation. But then if we start to do the calculation, so our formula is going to say this. The X normal stress is equal to negative my over I. Okay, we can calculate that I, we have an m. But what does that y mean? Yes, exactly. It's actually height above the neutral axis. Remember, this one is signed. But in this case, you get the same thing, that y value for this point A is 0. It's on the neutral axis. Okay? And so there's no reason to do any more calculations. A is on the neutral axis. So y is equal to 0. And therefore, the stress tensor due to bending is just zeros. And now we'll go to the shear force. So let's make sure that this meets the beam requirements for calculating shear force. So remember that for the stress due to shear force, there are only 2 types of things that we can calculate. Anyone remember what those are? So one is a rectangular cross section that's taller than it is wide. That doesn't apply here. The other one is circular, but there's one caveat. We can only do circular cross sections at the neutral axis. Okay? So we can do circular cross sections but only at the neutral axis. But we are at the neutral axis at this point A. So A is on the neutral axis, so this will work. Okay, so what's our formula? So we're going to have an XY shear stress, and it's going to be equal to negative V times Q over IB. Okay, so we have to fill some of these things in. We know that V is 1471.5. Q, so let's think about the shape. Our line of interest is this. And so this is our area. The centroid of the area is somewhere here. And this is our distance. And then Q is equal to the area times the distance.
Is the distance from the centroid to A? To
The
point?
centroid of the shaded area to the neutral axis.
Oh, to the
Yep. So A is pi r squared over, well, okay. I am glossing over something here. And this is actually going to make this a little complicated. So if it was a solid circular shape, everything I did there would be right. But it's not a solid circular shape. It's this. Okay. And so the area is half of, so it's like pi times 0.012 squared minus 0.01 squared divided by 2, or half of the area I calculated before. Stop telling me the news. So this is okay, pi times 0.012 squared minus 0.01 squared divided by 2. So that red area is 6.912 times 10 to the minus 5 meters squared. Yep. Yeah, because it's the area above your line of interest. And our line of interest is the neutral axis for the area for calculating Q. What? Why did we just choose that red shaded region instead of the whole thing? Because if you remember, the definition of Q is like this. So if you have a shape and you have the centroid here, then the neutral axis is like this. And then you also have a line of interest. So say that you're calculating it here. Okay. Then what you do is you take the area above the line of interest and you find the centroid of the area above that line of interest. Then this is your D. The red shaded area is your A, and you multiply those two together. In this case, our line of interest is the neutral axis. The point we want is on the neutral axis. Okay, so that's why.
Why wouldn't just like the middle of the circle over like the inner this? Why don't
Because because that inner part is not material here.
it's a
It's hollow. We only have the
like in
yeah. It's just a tube. So you only do this for where you have material. Now we also have to calculate the centroid of this shape. So for the centroid of this shape,
we would just subtract the two, the arc radius from the
yeah. So let's put our let's think of our origin here, okay? And we want to find the centroid of this. So we're going to find the centroid of the big outer semicircle, and then we're going to subtract the centroid of the little inner semicircle.
we already know that it's going to be along the y-axis.
We do, yep. So all we need is the y position, the height. So y is going to be equal to 1 over the area times the area of the big outer thing, which is pi times 0.012 squared, times the centroid of the big outer thing. Well, anyone happen to remember the formula for the centroid of a semicircle or a quarter circle?
Or is it like, or is it 2/3 R?
I think it's 4r over 3 pi. So we have 4 times the outer r over 3 pi. Those pi's cancel. That's nice. And then minus the area of the inner one that we're removing from it. So 0.01 squared times 4r for the little one over 3 pi. And the pi's cancel. And so we get that y above the neutral axis is 0.012.
Or why do you put the 1 over the area at the beginning?
That's the formula for centroid. We're just trying to calculate the centroid of this shape.
Oh,
And so I get that y here is equal to, oh, and then I have to divide by that area. 6.912 times 10 to the minus 5. Okay, so I get that y is equal to 0.01404. And that's our D for calculating Q. That's the distance from the neutral axis to the centroid of that shape. And yep.
We have like a false distance and the x, then we'll need to use Pythagorean here to find b.
We already have, this is the d. We just had to find, so we found the distance from the neutral axis, which is where I put my origin, to the centroid of that shaded black shape.
Okay. So it's always gonna be just distance and y, right?
Yeah, that's right. So this is 6.912 times 10 to the minus 5 times 0.01404. And so that's 9.707 times 10 to the minus 7. This is meters to the third power. Now we have to calculate I and B. I for this circular shape is pi over 4 times 0.012 to the fourth minus 0.01 to the fourth. That's another formula that you have in your notes. And so that is 8.432 times 10 to the minus 9. And this is meters to the fourth. And then the last one is the base. So that is the width of this thing at your line of interest. So at our line of interest, which is the neutral axis, that base is just 2 times the radius. Well, since this is, again, you have to consider the fact that this is not solid, it's hollow. So it's really just, this is like the material amount of resistance to this stress. So it's going to be 2 times so the base is going to be 2 times the quantity 0.012 minus 0.01. That's just that horizontal amount of material resisting this stress. And so that's 0.004 meters. And so now finally we can put this all together. Yeah. Oh.
Does the 2/3 times for Q 2/3 times RQ?
Oh, we could have used that, yes. Okay. Well, okay. So I gave you that formula thinking of a solid cross section. So you could derive something like that for a hollow thing, but I didn't do it. So that formula that I gave you won't work for the hollow. Yeah. So tau xy is equal to negative. Go back and find our V. 1471.5. Times our Q. 9.707 times 10 to the minus 7. Divided by our I, 8.432 times 10 to the minus 9. Times our base, 0.004. And this, I think, is going to be a pretty huge stress because I made the walls pretty thin on this. Well, not that big actually. So this is negative 4.235 times 10 to the 7 pascals. The one due to torque, I think, is going to end up being really big now that I think about it. So our stress tensor due to shear force is 0, negative 4.235 times 10 to the 7, 0, negative 4.235 times 10 to the 7, 0, 0, 0, 0, 0.
Wait, now, if you would wanna find like the principal stress tensor of that, would you just put that into like the calculator?
Yeah, I can't think of an application where you would just want to find it for this, but what you would likely want to find is once you add all of these together, you'd want to find the principal stress tensor of that. And yes, you would just add out all together, get this big stress tensor, and then find the eigenvalues of that. Okay, so the last one we need is the stress due to the torque. What are the beam requirements for calculating stress due to torque?
Can it be a circular cross section?
Yep.
Or a thin closed tube?
That's right, a closed thin-walled tube. This actually is both. We haven't learned to calculate stresses for thin-walled tubes yet, but we have for round, so we can just use the round approach. So the cross section is circular. So we can calculate, so we can use it. And we have that our stress tensor in our temporary coordinate system, or our XY shear stress in our temporary coordinate system, is equal to negative T times the distance from the centroid to our point of interest divided by the polar moment of inertia. And our internal torque was negative 1400, I think. And our rho, the distance from the centroid of the cross section to the point that we want, is 0.012. It's all the way out on the edge. That rho is always positive.
Oh.
And remember, we're in the temporary coordinate system, so it would be positive anyways. Because our temporary coordinate system is, well, I did it so our temporary is our permanent coordinate system, so we're not going to have to use a rotation matrix here. Are you with me on that? Because our temporary always has the z-axis pointing out to the point of interest. Okay, and the last thing we need is our polar moment of inertia. And the formula here is pi over 2 times 0.012 to the fourth minus 0.01 to the fourth and that is 1.686 times 10 to the minus 8 meters to the fourth. Um, okay, and so tau xy is equal to negative of negative 1400 times 0.012 divided by 1.686 times 10 to the minus 8. Which is 9.962 times 10 to the 8th. That's a big stress. This is pascals. And our temporary coordinate system is our permanent coordinate system. So this is also just tau xy in our usual coordinate system, the one we want.
V's going to the left.
Right. And so our stress tensor due to torque is 9.962 times 10 to the 8, 9.962 times 10 to the 8, zeros. Now add these all together, and our total stress tensor is, so for tension compression, we had 1.4469 times 10. Right, it is 14.469 megapascals. And then we have 996.2 megapascals minus 42.35 megapascals leaves you with 953.85. I'll pretend I didn't have the significant figures issue there, that we just knew all these exactly. 0, and then 953.85 zeros everywhere else. And this is in megapascals. Any questions about that? So now if you want, I don't remember exactly what it asked, the strain. So if you wanted the strain now, the Voigt strain would just be, it says it's for steel, so use a compliance matrix with the values for steel. And then we have, be careful of the units always when you use the compliance matrix. So this is 1.4469 times 10 to the 8. Then 0, 0, and then 0, 0, and then oh, this was to the 7, not the 8. And then this is 9.5385 5 times 10 to the 8. And those are really big stresses. Somebody asked me at the end of last class if there are any materials that can withstand, say, 1 gigapascal of stress. I said I didn't think so, but then we chat GPT'd it. And there are some fancy materials, high-tech materials that can withstand that much stress. Regular steel usually can't. It's very close to its limit. But carbon fiber can if you load it the right way. Some of these high-tech materials are very picky about how they're loaded. They have tremendous strength loaded in one direction, but not so much loaded in another direction. And there were a few, and I can't remember. There was one that was super, super high. I can't remember what it was, but. What? No, diamond is very stiff, but not very strong. So it will fail at a pretty low stress. But if you look at the stress versus strain graph that you would get from a tensile test, it's very, very steep. So
It's brittle, or is that the right term?
It is brittle, but it can't handle very much strain energy, which we haven't even talked about, but you can calculate this kind of like the stored, like think of a spring, like when you stretch it, there's an amount of potential energy in it. That's strain energy. And you can calculate strain energy for other materials, but of course we do it in 3D, not 1D. And so diamond is very stiff, has a very high Young's modulus, but it can't absorb much strain energy before it breaks. And so what was I talking about? Who knows?
The one that
1 gigapascal. What materials can withstand 1 gigapascal of stress? Only very carefully engineered materials. Okay, so remember when that sea exploring submersible imploded? So the big controversy with that, like a lot of people were raising major alarm bells before it finally failed. And what people were most concerned about was that this engineer, the owner of this, or the CEO at least of this company, was using carbon fiber for the hull. And he was using carbon fiber because it's very, very strong when it's loaded exactly as planned. And so carbon fiber is one of those few materials that can withstand gigapascal stresses. The problem is after you bring this stuff down, it compresses, it deforms in just very slightly unpredictable ways. And you start to get changes in shape, and then you start to get some little shear stresses instead of just being purely compressive and tensile. And as you start to develop those slightly odd little stresses, carbon fiber becomes very bad at doing its job. And that is what presumably happened. Stresses were introduced that weren't exactly perfectly loaded, and then, it couldn't withstand it. Okay. It also asked in this problem for the maximum absolute value of shear stress. So to do that, we might as well do it. It's fast. It's just plugging it into a calculator. So the principal stress tensor. Come on, you dummy. Oh. My computer's on break for a second. It'll come back.
So you calculate the principal stress from the total stress that you got.
Yes. So take that stress tensor that we just calculated. Okay, so that stress tensor that we just calculated, this one, we'll just take the eigenvalues of that. And so let me enter that. And now eigenvalues. What?
200.
Oh, for E in Young's modulus? Yeah, 200 times 10 to the ninth, and then 0.3. Bless you. There are different kinds of steel, and they all have slightly different numbers, but that's always a good middle sort of steel.
200 on what, sorry?
200 times 10 to the 9 for Young's modulus, and then for Poisson's ratio, 0.3. And so the principal stress tensor is 961.11, negative 946.64, and 0. This is megapascals. And so then the maximum shear stress is the maximum principal stress minus the minimum principal stress divided by 2 which is 953.88 megapascals. Okay, I'm going to make the soft call on this, and we won't do thin-walled tube stuff on the exam. And we'll just do the quiz now, and we'll just finish this stuff up after the exam. So no stress due to torque for thin-walled tubes. On exam 3.
Oh, right on the calendar.
Yeah.
And on that, the time and location been.
Yeah, I think I have those.
Sorry.
Oh, so anything that's circular, you can use the circular approach. This is also a thin-walled tube, and so once I talk about how to approach thin-walled tubes, we could use that for this, and we could see how similar those answers are, and the answers are very, very similar.
Some are gonna have the formulas for each stress,
Yeah.
and that's for the moment of order and Q and B or not.
What?
For Q, like on the shear stress.
Yeah, I'll give you all those. Yep, formulas for every one of those things you need.
Requirements.
I'm not going to give you beam requirements, but yeah, I'm not going to give you those. Those kind of things will come up on quizzes. I'm not going to try to mess with you on the exam on those.
Okay, so
You can just assume if I ask you for something that we have a way to calculate it.